We're starting chapter 3. This is section 3.1 called the derivative of a function. So the definition of a derivative. The derivative of a function f with respect to the variable x is the function f prime of x, whose value at x is, and this should look familiar, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h, provided the limit exists. Now you know that we have done something that looked like this in our last chapter, the limit as h approaches 0, and you don't have to write this down, of f of a plus h minus f of a over h. And we use this to find the instantaneous rate of change at a value x equals a. So we use this with a number in that a slot to find an instantaneous rate of change at a particular value. What we're doing now is we're going to leave that as an x and find a general equation for the instantaneous rate of change at any value x. And this equation, sorry about that, oh, it keeps jumping. This equation is called the derivative. So we're taking what we did in the last part of chapter 2, one more step. The domain of f prime, the set of points in the domain of f for which the limit exists, may be smaller than the domain of f. So in other words, we may not be able to find a derivative at every point of the function. However, if f prime exists, we say that f has a derivative or is differentiable at x. A function that is differentiable at every point is a differentiable function. So a function can be differentiable on part of its domain, or it can be differentiable on the entire domain. So let's look at an example. We're going to differentiate this function f of x equals x squared. So to find the derivative f prime of x, we take their function definition and we're going to plug in x plus h into our function value. So we get x plus h squared minus f of x, which is x squared, over h. We're going to continue that by FOILing out our squared binomial. Then we're going to simplify this. We can cancel the x squareds and factor out an h. These will cancel. We now have the limit as h approaches 2x plus h, which is 2x. So the derivative, f prime of x squared is 2x. We have just found an equation to find the derivative at any point on this function, or in other words, to find the instantaneous rate of change at any point on the function value. Okay, the derivative, this is an alternate definition using x and a instead of the other. Let me go ahead and write this down. The derivative of a function f at the point where x equals a is the limit f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. So again, this is an alternate definition. Let me just say that this one, the picture would look like this. We would have our function. This is where we want to find our value at a. And then we have some other random value x. And as x approaches a, they end up being on top of each other. And that, again, is our instantaneous rate of change. In our last example, we had our value x, and we had x plus h. and it was as h approached 0. Same idea, moving a point closer and closer using a limit to get an instantaneous rate of change at a point. So we can call the 2 points x and x plus h, or we can call them a and x and do the limit as x approaches a. We use the first one more often than the second one. Okay, notation. This is just a whole bunch of different ways to write f prime of x. So the function, the derivative of this function, f of x, besides f prime of x would be y prime, nice and brief, but it does not name the independent variable, dy dx, or the derivative of y with respect to x. It names both the variables and uses d for derivative. df dx, or the derivative of f with respect to x. This emphasizes the function's name. We will rarely use this. And then d dx of f of x. That means we're taking the derivative with respect to x of this function. So the ones we will use most often will be f prime of x, y prime, dy dx. We will use this once in a while. We will rarely use the other one, but put them all into your notes. Okay, relationship between the graphs of f and f prime. Because we can think of the derivative at a point in graphical terms as a slope, this is what we did in chapter 2, we can get a good idea of what the graph of the function of f prime looks like by estimating the slopes at various points along the graph. We estimate the slope of the graph of f in y units per x units. That's our delta y over delta x. That's our slope. We then plot the estimates in a coordinate plane. The function we just did, y equals x squared, and that was our function f of x. And we found that f prime of x equaled 2x. So let's take a look at that. 2x is a graph that looks like this. So using a different color of ink, let's look at the slopes of f of x squared. The slope at 0, horizontal tangent, is 0, and that's my function value for f prime. If I move a little bit further, my slope is maybe something like 1, if I draw a tangent line there. And if I move a little bit to the right, the graph of f prime of x has the point 1, 1. Well, actually, it would be 1, 2, but anyway. But you can see that as I go up and up, as my x value gets bigger, my slope value gets larger. And so as my x goes to the right, my slopes get bigger. To the left, I have big negative slopes on the left until I get close to 0, and they're little negatives. So again, the further out I go, I have big negatives, and they come all the way up to little negatives. Let's try one more. So here's a function in blue, and I'm going to look at some slopes again. So right here in the middle, I would say that this slope, and I wish they'd done the scale more evenly, this slope is going to be a negative number, and here it is right here at 0. Out here, this has a slope of 0, and you can see that the matching point on this graph, f prime, has a value of 0 at this x value. There is also a tangent line that has a slope of 0 here, and if I look down here, I also have a slope of 0. All of the slopes between here and here are negative slopes. Little tiny negatives, bigger negatives, and then again, smaller negatives. Small negatives, big negative, small negatives. And the slopes going up the right side, the further up I go, the steeper the slope is, and on my slope graph, the further off I go to the right, the bigger my positive number gets. We will do a whole lot more with this shortly. Okay, discrete points plotted from sets of data do not yield a continuous curve. So if I just have a bunch of data points, let's say they look something like that. So this is a scatter plot. It's often possible to fit a curve to the points using regression. We talked about best fits. However, it's also possible to get a scatter plot of the derivative from data by computing slopes between the points. So if this is all I have to go by, I can find a slope between these 2 points. Let's say that's a slope of 2. And on my derivative graph at this point, I would have a value of 2. So I can find slopes between 2 points to estimate my derivative. All right, one-sided derivatives, like one-sided limits. The function y equals f of x is differentiable on a closed interval a to b if it has a derivative at every interior point, calculated the way we talked about at the beginning of the video, and if the limits at the end points exist. So a is the left end point of this. So there's my a. So if I am approaching, as h is getting smaller and smaller from the right, if I can find a limit at a, that's called the right-hand derivative. At b, point B, I would have to be approaching it from the left. H would have to come from this side and move closer and closer. And that would be my left-hand derivative. From the right, from the left. So in the right-hand derivative, h is positive and a plus h approaches a from the right. So here's my a plus h, and it's approaching it from the right only, and the same on the right-hand side. So a left-hand and a right-hand derivative, remember again, the right-hand derivative approaches from the right, it's not the right side of the graph, and the left-hand derivative approaches from the left, and it's not the left side of the graph. If you have questions about that, ask me. Right-hand and left-hand derivatives may be defined at any point in the function's domain. And the usual relationship between one and two-sided limits holds for derivatives. So we can conclude that a function has a two-sided derivative at a point if and only if the function's right-hand and left-hand derivatives are the same. So if I have a point here, if the derivatives coming from both sides are the same, we assume that the derivative exists. Okay, so we're going to show that the function has a left-hand and right-hand derivative at 0, but no derivative at that point. So here's our function that we're going to use. So the left-hand derivative, now, coming from the left, we are going to be using the top function, because the top function happens everything over here. So when x is less than 0, so in order to get to 0, I'm going to be coming from the left towards 0. This function is everything on the right hand of the graph, so I'm going to be coming from the right. So this is my left, this is my right, this is negative x, this is x. So negative 0 plus h minus 0, that's my function value, my a plus h minus f of a, and I get negative 1 for this. The right-hand derivative, same thing but using the positive x, and I end up with positive 1. So there is a limit from the left, it is negative 1. There is a limit from the right, it is positive 1. However, the derivative at 0 does not exist. Now, hopefully you recognize this function as the definition of an absolute value function. So, anything to the left, less than 0, has a left-hand derivative coming this way as I approach 0 of negative 1. Everything over here has a right-hand derivative of positive 1. There is no derivative at x equals 0. I cannot draw a tangent line here. I know it looks like the slope should be 0 here, but it is not, because everything closer and closer and closer has a slope of 1 to the right. Everything closer and closer has a slope of negative 1 to the left. There is no derivative. Oh, well, that's it. I thought I had one more slide. So that's it, and we'll see you in class.